Lattice energy is energy required to separate one mole of solid ionic compound into ions in the gaseous state. It determines the stability of an ionic compound. The general format is we write the ions in the reactant side and the solid ionic compound on the product side. It is determined to be exothermic. So when the ions bond together, energy is released. Delta H, or energy on the product side, is exothermic. Energy on the reactant side is endothermic. If we're considering lattice energy as a trend of the periodic table, as I go across left to right, lattice energy increases. As I go up the periodic table, lattice energy increases too, and it's dependent on the radius and the charge of the atoms when it becomes an ion. The general formula for lattice energy is E is equal to KQQ over R. Q plus is the charge of the cation, Q minus is the charge of the anion, R is the distance between the two ions. K is a constant. This equation looks very similar to Coulomb's law, in which force is equal to K times charge of 1 times charge of 2 over R squared. Just like Coulomb's law, we will not be doing calculations. However, you should understand the relationship. Lattice energy E is directly related to the charges. So the greater the charges of the ions, the greater the lattice energy. Lattice energy is inversely related to R. That means the greater the R, the distance between the two ions, the smaller the lattice energy, and vice versa. So if I go back to the trends, as I go across from left to right on the periodic table, the radius gets smaller. As the lattice energy goes up the periodic table, the atomic radius decreases again. Energy and radius are inversely related. From the lattice energy equation, you could determine the factors that affect the lattice energy. One is the charge. The greater the charge of the ion, the stronger the lattice energy. Ionic bond is held tighter. Size of the atom also affects the lattice energy. Bonds are stronger when ions are smaller because lattice energy and radius are inversely related. So determine the compound with the highest lattice energy. Pause the video, use the two factors or the lattice energy equation to determine which one has the higher lattice energy. Then check your answer. For A, calcium fluoride or sodium chloride, the one with the higher lattice energy will be calcium fluoride. Calcium has a charge of 2 plus, fluorine has a charge of minus, sodium has a charge of plus, chlorine has a charge of minus. So already calcium has a greater charge. Fluorine is much smaller than chlorine. Na is little smaller than calcium. However, the charge is much greater. For B, we have calcium iodide and calcium bromide. So we could ignore the calcium because they're the same, so they're both going to have the same charge and they're going to have the same size. Iodine is a -1 charge, so is bromine. So that means we have to look at the size. Smaller the negative ion will have the higher lattice energy. According to the ionic radius trend, bromine and iodine are in the same family. As I go down, it gets larger, so bromine is the smaller one. So calcium bromide is the smaller compound with the higher lattice energy. So here we have rubidium nitride and rubidium phosphide. Rubidium has a charge of plus, nitrogen is a 3 minus, rubidium again has a plus, phosphorus has a charge of 3 minus. We could ignore the rubidium because they're the same in both, so they're going to have the same radius as an ion. So we need to look at the anion. Nitrogen and phosphorus are in the same family, As I go down the periodic table, the ion gets larger. Nitrogen is the smaller ion. Rb3N is the smaller compound, so it will have the highest lattice energy. Next, we have cesium chloride and magnesium oxides. Cesium is a plus, chlorine is a minus, magnesium is 2 plus, oxygen is 2 minus. If I compare the size of my cation, magnesium is much smaller because it is in period 3, while cesium is in period 6. Chlorine and oxygen, chlorine is in period 3, oxygen is in period 2, so oxygen should be a little bit smaller. However, since magnesium and oxygen have a greater charge, this will have the highest lattice energy. For lattice energy, you need to understand the relationship of the equation. You will not give values to calculate lattice energy, but you need to understand E is proportional to the cation charge and the anion charge multiplied, and inversely proportional to the distance between the ions. Bulk of this chapter will be spent on Lewis dot structure, which is a diagram that represents the valence electrons of an atom or ion or a compound. Electrons will be represented by dots. Therefore, you need to draw your dots correctly. If it's not a dot, you need to erase it, or it will be counted as a dot. As we learned in the previous chapter, there are two main types of bonds. Ionic bonds are between metals and nonmetals, exist by transferring electrons. The cation donates, the metal donates. That's why it becomes positive. Nonmetal receives or accepts, becomes an anion, and becomes negative. The second type of bond is covalent bond, which is between a nonmetal and a nonmetal, and they are formed by sharing electrons. And the sharing of electron is not always equal, as we learned through electronegativity. To draw the Lewis dot structure for ionic bonds, the first thing you want to do is determine the number of valence electrons. And then you're going to follow Hund's rule and then Pauli exclusionary principle to fill their outer shells. So if I have an element X, I write my symbol X and I count the number of valence electrons. We know the valence electrons are present in the S and the P block. S, there is 1 orbital. P, there is 3 orbitals. A total of 4 orbitals occupies the valence electron. For ionic bonds, there are 4 orbitals. 1, 2, 3, 4. If X has 7 valence electrons, we pick a starting point, and it doesn't matter which place we start. If I start up here, I put 1 electron following Hund's rule, and I could go clockwise or counterclockwise. I just need to go in the same order. So according to Hund's rule, there's 1 electron per orbital before pairing. So I'm going to do 2, 3, 4, and then I'm going to use Pauli's principle and pair in the opposite direction. 5, 6, 7. So we don't use the Alboff. We use only Hund's. So we fill in the S and P together. So if the element has 5 valence electrons, I'm going to start at the bottom and I'm going to go counterclockwise. 1, 2, 3, 4. Following Hund's rule. Pauli 5. So this is correct Lewis dot structure for element X if it has 5 valence electrons. So ionic bonds consist of a metal and a non-metal. So we find the valence electrons for the metal, and then we find the valence electrons for the non-metal. Lithium has 1 valence electron. If I draw the Lewis dot structure for lithium, it looks like this. Lithium with 1 dot, or 1 valence electron. Chlorine has 7, so I'm going to use Hund's and Pauli's. So 1, 2, 3, 4, 5, 6, 7. I just drew the Lewis dot structure for lithium atom and chlorine atom. But when lithium bonds with chlorine, lithium takes a +1 charge and chlorine takes a -1 charge. What happens is during bond, when lithium bonds, because it's a metal and it's easier to give off 1 electron than take in 7, it takes that 1 electron and gives it to the chlorine. And the chlorine atom will take that 1 electron and become a negative ion. We write this as Li becomes a plus, and it has no valence electron, and then chlorine will have 8 valence electron, be a minus. So magnesium has 2 valence electrons, so Mg, so 1, 2, that's neutral magnesium. Oxygen has 6 valence electrons, so it's going to be 1, 2, 3, 4, 5, 6. Magnesium, when it bonds, likes to take a 2+ charge. Oxygen likes to take a 2- charge. Magnesium gives off the 2 electrons because it's easier to give off 2 than take in 6, while oxygen needs to fulfill its octet rule. One of the magnesium electron goes to the oxygen, that is unpaired electrons, and then the other one goes to the other unpaired electron. So my new structure after it's bonded, Mg has no valence. It's going to be 2+ on the outside with brackets, and then oxygen will have a full octet with a -2 charge and bracket. So pause the video, draw the Lewis structure for the following, and then check your answer. 1 aluminum has 3 valence electrons, so Al, 1, 2, 3. Oxygen has 6 valence electrons, 1, 2, 3, 4, 5. Metals like to give, so that means aluminum's going to give to oxygen. One of the electrons will go to its unpaired. Another one of aluminum's electron will go to the unpaired. Now oxygen is completely filled. It cannot take in another electron from aluminum. So where does the leftover electron from aluminum go? That means there is another oxygen. The leftover electron from the aluminum will go to the oxygen. Aluminum now has no more electrons to give. It gave away all its 3 valence electrons. However, my second oxygen did not fulfill the octet rule. That means there is another aluminum element. There is another aluminum atom present. It still has 3 valence electrons. It's going to give one of the valence electrons to this oxygen, and when it does, the oxygen is fulfilled and it's happy. Since aluminum has 2 more electrons left over, that means there is an extra oxygen. So oxygen is 1, 2, 3, 4, 5, 6. Aluminum is going to give away its second electron to the unpair, and then the last electron to the unpaired oxygen atom. Aluminum is happy once it gives away the 3 valence electron. Lower energy level has 8 electrons and it fulfills the octet rule. Oxygen is also happy because it took in 2 and now it has 8 and it fulfills the octet rule. So if I write this is going to look like aluminum with no valence electron. Oxygen is going to have a full valence electron shell, or we can make it a little simpler. There's 2 Al 3+. There are 2 Al 3+, and then there's 3 oxygens with full octet 2-. And this is correct. When we write our nomenclature, aluminum has a charge of 3, oxygen has a charge of 2. I cannot reduce. So when I crisscross down, this becomes Al2O3. So when I bond, I need 2 aluminum atoms that become ion, and I need 3 oxygen, and that's what we have in the bonding. Rb has 1 valence electron. Nitrogen has 5. 1, 2, 3, 4, 5. Rb gives away its 1 valence electron to nitrogen, and it's happy because once it gives it away, the next lower energy level has a full octet. However, nitrogen is not happy. It needs 2 more valence electrons to be happy. So that means we have another Rb that Rb will also give away its one valence electron to nitrogen. Rb again is happy because it gave away that one valence electron, but nitrogen still needs one more because now it only has 7. So that means there's an extra Rb with one valence electron. It's going to give that one away to nitrogen. So when it does that, Rb is happy. Nitrogen is now happy because it has a fulfilled octet rule. If I rewrite this, Rb has no valence electrons. So it's just a positive, and there's 3 of them. Nitrogen has a full valence electron. There's only 1 of them. And this is a 3 minus. And if I wrote the nomenclature for Rb and N, charge of Rb is 1, N is 3. If I crisscross my charge down, the 3 comes down here, the 1 comes down here, becomes Rb 3, N 1. So I need 3 Rbs to 1 N. So the Lewis dot structure for ionic bonds involves a metal and a nonmetal. Find the valence electrons of each of the atom before they bond. The metals will give away its valence electron to fulfill its octet rule by going to the next lower energy level. Nonmetals will take in the valence electrons to fulfill its octet rule. You need to show the transfer of electrons and then rewrite your equation, the ion format, using brackets and charges on the outside. The metals should have no valence electrons in the bracket, while the nonmetals should have a full shell inside the bracket.